In 1960, a young radio astronomer named Frank Drake pointed a 26-meter dish antenna at two nearby stars and listened, not metaphorically, literally listened. He tuned the receiver to a frequency of 1,420 megahertz, the frequency at which neutral hydrogen emits radio waves, the frequency that he and his colleague Philip Morrison had argued any technologically advanced civilization would know about and might use to signal others. He listened to Tau Ceti and Epsilon Eridani, two sun-like stars within 12 light years of Earth, for approximately 150 hours over several months, and he heard nothing. No pattern in the noise. No repeating signal, no sign of anyone. That was 65 years ago. Since then, we have built larger dishes, more sensitive receivers, better signal processing algorithms, more sophisticated search strategies. We have covered more of the sky, more of the frequency spectrum, more of the possible modulation schemes that a signal from another civilization might use. We have surveyed millions of stars. We have monitored the galactic center. We have looked for optical signals as well as radio signals, for laser pulses, for infrared excess from Dyson spheres, for chemical signatures in planetary atmospheres, for any of a dozen other proposed technosignatures that a technological civilization might produce. And in 65 years of increasingly sensitive, increasingly comprehensive searching, we have found nothing. Not a whisper, not a pattern, not a single signal that has survived scrutiny as a genuine artifact of another intelligence. The silence is total. It is the most complete negative result in the history of science. And I want to tell you why I think that silence is the most important fact about the universe that we currently know. Not because it is evidence that we are alone, though it might be. Not because it proves that technological civilizations are rare, though they might be. But because the specific character of the silence, the way it fails to fill the space that the physics says should be filled if civilizations were common and long-lived, tells us something precise and uncomfortable about what happens to civilizations that develop technology, something that the data is not yet able to distinguish between several deeply disturbing interpretations. Something that I think every human being alive today, given what we know about our own civilization's current trajectory, should be thinking about very carefully. The silence of the universe is not empty, it is saturated with the absence of something that should be there. And the absence, read correctly, is one of the most important messages the cosmos has ever sent us. Let me start with the arithmetic, because I think the arithmetic is what gives the silence its weight. The Milky Way galaxy contains somewhere between 200 and 400 billion stars. Observations from the Kepler Space Telescope and subsequent surveys have established that roughly 1 in 5 sun-like stars has a planet in its habitable zone, the region where liquid water can exist on the surface. Applying this to the Milky Way, there are something like 40 billion potentially habitable planets in our galaxy. The galaxy is approximately 13 billion years old. The Sun formed 4.6 billion years ago, making it a relatively young star in a galaxy that has been forming stars for nearly 3 times as long. There are stars in the Milky Way that formed 8, 9, 10 billion years before the Sunday. Any civilization that developed on a planet around one of those older stars had a head start on us of billions of years. Billions of years. I want you to feel the weight of that number in the context of technological development. We have had radio technology for roughly 150 years. In 150 years, we went from the first wireless transmissions to a global communication network, space travel, nuclear weapons, genetic engineering, and the beginnings of artificial intelligence. In 1,500 years, a civilization with our trajectory would be barely recognizable to us today. In 15,000 years, incomprehensible. In 150,000 years, so far beyond our current state that we cannot begin to model it. And in 1 billion years, a civilization that did not destroy itself would have had time to develop and deploy technology at scales that dwarf anything we can currently conceive. A civilization 1 billion years old, assuming it survived and continued developing, would be capable of things that look like physics rather than engineering, restructuring star systems, moving stars, harvesting the energy of entire galaxies, spreading through the galaxy at a fraction of the speed of light over millions of years. Even without faster-than-light travel, a civilization expanding at 1% of the speed of light would colonize the entire Milky Way in roughly 10 million years. 10 million years is less than 1/10 of the age of the galaxy. A civilization that originated anywhere in the Milky Way and began expanding even 10 million years ago would have had time to reach every star in the galaxy and back multiple times over. The physicist Enrico Fermi first formalized this observation in a question he asked his colleagues at lunch in 1950 at Los Alamos. If the universe is as old and as large as it appears, if intelligent life can arise, and if civilizations tend to expand, then the galaxy should be full of evidence of those civilizations. We should be visited. We should be colonized. We should be receiving signals. We should see megastructures, stellar engineering, the unmistakable signs of intelligence operating at civilizational scales. And yet, Fermi noted, gesturing at the sky, we see nothing. Where is everybody? The physicist Enrico Fermi first formalized this observation in a question he asked his colleagues at lunch in 1950 at Los Alamos. If the universe is as old and as large as it appears, if intelligent life can arise, and if civilizations tend to expand, then the galaxy should be full of evidence of those civilizations. We should be visited. We should be colonized. We should be receiving signals. We should see megastructures, stellar engineering, the unmistakable signs of intelligence operating at civilizational scales. And yet, Fermi noted, gesturing at the sky, we see nothing. Where is everybody? Before going into the possible explanations for that silence, I want to make the quantitative case for why the silence is so surprising. This requires walking through what is called the Drake equation, even though calling it an equation is somewhat generous, since several of its terms are almost completely unknown. Frank Drake, the same astronomer who conducted the first SETI search in 1960, wrote down the equation in 1961 as a framework for organizing a scientific discussion about the probability of detecting extraterrestrial intelligence. It has been a fixture of the field ever since. The Drake equation says that the number of civilizations in the galaxy currently capable of transmitting detectable radio signals is equal to the product of the rate of star formation in the galaxy multiplied by the fraction of stars that have planets, multiplied by the average number of planets per solar system that could support life, multiplied by the fraction of those planets on which life actually develops, multiplied by the fraction of life-bearing planets on which intelligence develops, multiplied by the fraction of intelligent species that develop technology capable of producing detectable signals, multiplied by the average lifetime of such civilizations. Drake's original estimates gave a number somewhere in the range of 10 to 10,000 simultaneously transmitting civilizations in the Milky Way. Even the most pessimistic estimates consistent with his original values gave at least one civilization, presumably ours, and the most optimistic estimates gave numbers large enough that we should expect signals from multiple directions simultaneously. But here is what makes the Drake equation interesting rather than just historical. We now know from Kepler and other surveys that the first three terms in the equation are much more favorable than Drake originally assumed. Virtually all stars have planets. A substantial fraction of those stars have planets in the habitable zone. The conditions for life, at least the conditions that produce life on Earth, appear to be common. The astronomical factors in the Drake equation are not the limiting factors. The limiting factors are the biological and civilizational ones. What fraction of life-bearing planets develop intelligence? What fraction of intelligent species develop technology? And most crucially, what is the average lifetime of technological civilizations? This last term is the one that most directly connects to the Fermi paradox, because it is the one that most directly affects whether those civilizations are detectable. A civilization that transmits for 1,000 years and then goes silent leaves a window of detectability of roughly 1,000 years out of the billions of years of galactic history. A civilization that transmits for 1 billion years would be much easier to find. If technological civilizations typically transmit for only a few hundred years before either going silent or going extinct, the number of civilizations currently transmitting in the galaxy could be very small, even if civilizations are relatively common in the sense of having developed at some point in galactic history. The silence would then be the silence of civilizations that each had a brief window of detectability and are now quiet, either because they destroyed themselves, stabilized at a non-transmitting level, or deliberately chose silence. This is the Fermi paradox. And it is not really a paradox in the logical sense. It is a gap, a discrepancy between what we would expect to observe if technological civilizations are common and long-lived and what we actually observe, which is nothing. Something is wrong with one of the assumptions. Either civilizations are not common, or they are not long-lived, or they are not expanding, or they are hiding, or there is something else wrong that we have not identified. The silence is the data, and the data demands an explanation. I want to walk you through the major categories of explanation because they are not all equally compelling and they do not all have the same implications. Some of them are reassuring, some are deeply disturbing. And one of them, the one I think the evidence currently most supports, is the kind of thing that once you understand it, you cannot look at human civilization the same way again. The first category of explanation is what physicists call the rare earth hypothesis. The idea that the specific conditions required for the development of complex life are so numerous and so improbable that intelligent life, despite the vast number of planets in the galaxy, is extraordinarily rare, perhaps even unique to Earth. The rare earth hypothesis has many versions, but the most sophisticated version, developed by paleontologist Peter Ward and astronomer Joe Kirkland in their 2000 book of the same name, argues that the development of complex multicellular life requires a specific combination of conditions that goes far beyond simply having a planet in the habitable zone. The planet needs to be in the right region of the galaxy, not too close to the violent center, not too far from the metal-rich inner disk. It needs a large moon to stabilize its axial tilt, preventing the wild swings in climate that would disrupt the development of complex ecosystems. It needs a Jupiter-like gas giant in an outer orbit to deflect the bombardment of comets and asteroids that would otherwise sterilize the surface. It needs plate tectonics, driven by radioactive heating of the interior, to recycle nutrients and maintain the carbon silicate cycle that regulates the long-term climate. It needs the right kind of star, not too variable, not too luminous, not too small and flare-prone. Each of these conditions is individually plausible. Each individually is met by a significant fraction of planetary systems. But the conjunction of all of them, the specific combination required for the development of complex life, may be extremely rare. If only 1 in a billion planetary systems meets all the criteria, the number of planets in the galaxy capable of developing intelligent life might be small enough that we genuinely are alone, or nearly alone, in the Milky Way. The rare earth hypothesis is scientifically serious. It is not pseudoscience. It draws on genuine astronomy, geology, paleontology, and evolutionary biology. But it has significant problems. The more we learn about extrasolar planetary systems, the more diverse they appear. Some of the specific conditions Ward and Kirkland identified as necessary have been found to be relaxed. Moons larger than ours have been found. Planets in stable orbits in the habitable zones of a variety of star types have been found. The specific conditions that seem necessary on Earth may be one pathway to complex life rather than the only pathway. Life, as we are learning, is more robust and more creative in its mechanisms than we assumed. More fundamentally, the rare Earth hypothesis, even in its strongest form, does not fully resolve the Fermi paradox. Even if complex life is rare, if it arises only once per 1,000 galaxies rather than once per star system, there are 2 trillion galaxies in the observable universe. Even at that rate, the number of civilizations that have ever developed in the observable universe is on the order of 2 billion. 2 billion civilizations, some of them billions of years old, and we see nothing. The rare Earth hypothesis reduces the number of civilizations, but does not explain the absence of the oldest, most advanced ones whose signals or structures should be detectable across enormous distances. The second category of explanation is the Great Filter. This concept was developed by economist Robin Hanson in a 1998 paper and has been developed and refined by many researchers since. The Great Filter is the idea that somewhere in the progression from lifeless matter to galaxy-spanning civilization, there is a step that is so difficult, so improbable, so lethal, that almost no lineage of matter ever gets through it. Some filter that almost all would-be civilizations fail to pass. The crucial question about the Great Filter is where it is. Is it behind us or ahead of us? If the Great Filter is behind us, if the hard step has already been passed by our lineage, then we are rare survivors. We got through the filter, most planets did not. The silence of the galaxy is because the filter eliminated almost everyone, and we are among the vanishingly few that made it. This is actually a somewhat comforting interpretation, because it means the future is open. Having passed the filter, we might go on to become one of those long-lived, galaxy-spanning civilizations. The silence is not ominous. It is just loneliness. If the Great Filter is ahead of us, if the hard step is something that technological civilizations have not yet faced, then the silence is terrifying. It means that civilizations like ours, civilizations that have developed technology and begun to influence their planets, almost always fail to survive. They develop technology, they reach something like our current level, and then something destroys them. The silence of the galaxy is a cemetery. Every potential civilization in it has run into the filter ahead and been stopped. And we are running toward that same filter right now. What could the Great Filter ahead be? The candidates are as familiar as they are disturbing. Nuclear war, climate change so severe that industrial civilization collapses before it can be stabilized, a pandemic produced by biotechnology or by natural evolution that exceeds our ability to respond, artificial intelligence that develops goals misaligned with human survival, resource depletion, environmental degradation that cascades into civilizational collapse. Any of these, or some combination, or something we have not yet imagined. The filter does not need to be a single dramatic extinction event. It might be more subtle. Civilizations might not be destroyed suddenly. They might simply reach a certain level of technological development and become unable to sustain the growth and expansion that would be necessary to become detectable across interstellar distances. They might collapse back to lower technological levels from which they cannot recover. They might develop technologies that are highly destructive locally, but not dramatic enough to be detectable across light years. They might persist in a diminished, unsustainable state before eventually fading out. The filter, in other words, might look a lot like what we are currently experiencing. A civilization that has developed technology sufficient to affect its own planet, that has created weapons capable of ending complex life, that is altering its climate in ways that threaten its stability, that is producing knowledge and capabilities faster than its social and political institutions can manage. A civilization at a transition point between the level of technology it currently has and the level required to secure its long-term future. A civilization that is not necessarily doomed, but that is facing a test of whether it can manage the specific combination of challenges that technology creates. Most civilizations that reach this transition, the silence suggests, do not pass the test. I want to stay with the filter concept a little longer, because I think the most important version of it is one that gets less attention than it deserves. Most discussions of the Great Filter focus on dramatic existential risks, the big wars, the runaway AI, the civilization-ending pandemic. But there is a subtler version that I find more compelling as an explanation for the specific character of the silence we observe. Consider what a civilization needs to do to become detectable across interstellar distances. It does not need to be trying to signal. It just needs to be operating at a scale that produces detectable byproducts. A civilization using the energy of its star through a Dyson sphere, a structure that captures a significant fraction of stellar energy output, would produce an infrared excess detectable across thousands of light years. A civilization engaged in interstellar travel would produce detectable signatures in the form of electromagnetic emissions from propulsion systems. A civilization building megastructures around stars would produce observable transits. A civilization doing nothing more exotic than continuing to expand its energy use at the rate human civilization has expanded it for the past century would eventually become detectable. The specific problem is not just survival. It is the combination of survival and continued growth. A civilization that survives but stabilizes at a low energy level. A civilization that reaches technological capability and then consciously or unconsciously chooses to live within planetary means rather than expanding would not be detectable. It would be present but invisible. And this may be the most common outcome of civilizational development. Not extinction, but limitation. Not destruction, but the choice, forced or voluntary, to live sustainably within a planetary system rather than expanding to stellar scales. This possibility has a name in the literature, the sustainability solution to the Fermi paradox. Civilizations exist, but they do not expand indefinitely. They reach a stable configuration and stay there. They are not detectable because they are not broadcasting, not expanding, not building megastructures. They are just living quietly within their means. This solution is less dramatic than the extinction hypothesis, but it may be more accurate, and it has a specific implication for our own situation that I think is important to name directly. The civilizations that survive may be precisely those that learn to limit their expansion, to live sustainably within a planetary system, to treat technological capability as a tool for flourishing within constraints rather than as an engine for unlimited growth. The ones that do not learn this either destroy themselves or become detectable. And we see no detectable civilizations. There is a version of the SETI silence that is not about death but about wisdom. The old civilizations are out there. They are just quiet. Not because they are hiding, not because they are extinct, but because the long-lived ones learned something that the young ones have not yet learned. That the universe is not a resource to be consumed, but an environment to be inhabited. This solution is less dramatic than the extinction hypothesis, but it may be more accurate. And it has a specific implication for our own situation that I think is important to name directly. The civilizations that survive may be precisely those that learn to limit their expansion, to live sustainably within a planetary system, to treat technological capability as a tool for flourishing within constraints rather than as an engine for unlimited growth. The ones that do not learn this either destroy themselves or become detectable, and we see no detectable civilizations. There is a version of the SETI silence that is not about death but about wisdom. The old civilizations are out there. They are just quiet, not because they are hiding, not because they are extinct, but because the long-lived ones learn something that the young ones have not yet learned. That the universe is not a resource to be consumed, but an environment to be inhabited. But I want to address two other solutions that get significant attention and that I think are less convincing but important to engage with honestly. The first is what is sometimes called the zoo hypothesis, proposed by the astronomer John Ball in 1973. The zoo hypothesis says that advanced civilizations are aware of us and have deliberately chosen not to contact us. We are, in Ball's metaphor, animals in a zoo, observed but not interfered with. The advanced civilizations have established a policy of non-interference, perhaps to allow us to develop naturally, or perhaps to study us, or perhaps for reasons we cannot currently comprehend. The zoo hypothesis has emotional appeal. It explains the silence without requiring that civilizations are rare or self-destructive. It fits a certain narrative about the relationship between less and more advanced civilizations. But it has a significant logical problem. The zoo hypothesis requires that every advanced civilization in the galaxy has adopted and maintained this policy without exception. A single civilization that decided to make contact even once would break the zoo. And it requires that the policy has been maintained for the entire duration of our civilization's detectable existence, roughly 100 years of radio emissions and 4 billion years of biological evolution if any civilization was monitoring our planet before we developed technology. The probability that every advanced civilization in the galaxy, without exception, has independently adopted and maintained a strict non-interference policy for billions of years strains credulity. Organizations of any kind do not maintain perfect unanimity over long timescales. If there are thousands of advanced civilizations, the probability that none of them has ever defected from the non-contact policy in the past billion years seems vanishingly small. The second solution that deserves engagement is the dark forest hypothesis, named after the Chinese science fiction novel by Liu Cixin. The dark forest hypothesis says that the universe is silent because advanced civilizations deliberately eliminate any other civilization they detect. The logic is game theoretic. In a universe of finite resources and uncertain intentions, the detection of another civilization is a threat. You cannot be certain that the other civilization is benign. The safest strategy is to destroy it before it can destroy you. Civilizations that survive are those that learn this lesson and act on it. The universe is a dark forest in which every civilization moves silently and shoots first. The dark forest hypothesis is genuinely disturbing, which is part of its appeal as science fiction, but as science, it has problems. It requires that every advanced civilization in the galaxy has independently arrived at this aggressive strategy, which seems unlikely given the diversity of circumstances in which civilizations develop. It also fails to explain the absence of megastructures. A civilization engaged in the dark forest strategy would presumably still build megastructures for its own use. The dark forest strategy explains the silence of radio transmissions, but not the silence of the galaxy's large-scale structure. I find the more mundane explanations more compelling, not because they are more comforting, but because they are more consistent with the full scope of the silence. I want to be honest that I am now well into the speculative end of the spectrum. The physics of the Fermi paradox is real and rigorous. The interpretation of the silence is not. There are many possible explanations, and we cannot currently distinguish between them with the evidence we have. What I am giving you is not a scientific conclusion, but a reading of the data that I find compelling given everything else we know. Let me now take you into the specific searches that have been conducted and what they have found, because I think the details of the search are important for assessing the significance of the silence. The SETI Institute has been conducting systematic searches for radio signals from technological civilizations since the 1980s. The Allen Telescope Array in California, the largest dedicated SETI telescope complex in the world, consists of 42 small dishes that can be combined to observe specific target stars while simultaneously monitoring a large patch of sky. It has surveyed tens of thousands of star systems in detail. The Greene Telescope in West Virginia and the Parkes Telescope in Australia have been used for SETI observations that have surveyed millions of stars. The Breakthrough Listen initiative, funded by Yuri Milner and announced in 2015, has been the most comprehensive SETI search in history, using the Greene Telescope and the Parkes Telescope to survey the 1 million nearest stars, the 100 nearest galaxies, and the entire plane of the Milky Way. Let me give you a sense of the scale and sensitivity of these searches. The Breakthrough Listen program can detect a signal equivalent to the output of an ordinary airport radar at a distance of several light years. It can detect a signal equivalent to the Arecibo radar, one of the most powerful transmitters humans have ever built, at a distance of several hundred light years. Its sensitivity has improved by many orders of magnitude compared to Drake's first search in 1960. If a civilization within a few hundred light years of Earth were deliberately transmitting toward us with a transmitter comparable to what we could build today, we would almost certainly have detected it. The searches have also extended far beyond radio. The optical SETI program searches for nanosecond pulses of laser light from other stars, which a civilization might use for interstellar communication, because laser pulses can be made extraordinarily bright for very brief durations, bright enough to outshine a star for that instant. The GAT project, the Glimpsing Heat from Alien Technologies project, led by Jason Wright at Penn State, searched nearly 100,000 galaxies for the infrared excess that would indicate galaxy-scale energy use by a Kardashev Type 3 civilization. The Tabby's star phenomenon, formerly known as KIC 8462852, generated enormous excitement. In 2015, when astronomer Tabitha Boyajian discovered that it was dimming in irregular, asymmetric ways that standard stellar physics could not easily explain. For a period of months, it was the leading candidate for a Dyson sphere or other megastructure under construction. Subsequent analysis of archival data and dedicated follow-up observations revealed that the dimming was consistent with circumstellar dust, likely from a recent disruption of cometary material, not aliens, disappointing in one sense, but scientifically important because it showed how seriously the community takes these candidates and how rigorously it pursues them. There have been other tantalizing anomalies over the years. The WOW signal in 1977, which I discussed in the earlier video on radio signals and which remains the best candidate for an extraterrestrial signal we have ever detected, though almost certainly with a natural explanation. The curious clustering of fast radio bursts in certain directions that briefly suggested a possible source related to the galactic center. The anomalous radio signal from the star Ross 128 in 2017, a nearby red dwarf that turned out to be interference from a human satellite, and the more recent BLC-1 candidate signal from Proxima Centauri, the nearest star to the Sun at 4.2 light years, which generated significant press attention in 2020 before being identified as radio frequency interference of terrestrial origin. Each of these cases follows the same pattern. Anomaly detected, community mobilizes, multiple independent observations conducted, natural or artificial terrestrial explanation found, deflation. The process is not a failure. It is science working correctly. The community is not dismissing anomalies prematurely. It is subjecting them to exactly the scrutiny that extraordinary claims require, and none has survived that scrutiny. These searches have generated enormous amounts of data. The Breakthrough Listen program alone produces petabytes of data per year, and the signal analysis has become increasingly sophisticated. Machine learning algorithms can now identify patterns in radio data that human analysts would miss. The sensitivity of the searches has improved by many orders of magnitude since Frank Drake's first observations in 1960. We can now detect signals that would have been completely invisible to the instruments of the 1960s. And the result is silence. Thousands of candidate signals that turned out to be interference, equipment, artifacts, or natural sources. And no confirmed signal from another civilization. The wow signal, which I discussed in an earlier video in this series, remains the best candidate. A 72-second burst of radio emission at 1,420 megahertz, detected by the Big Ear telescope at Ohio State University in 1977, with properties consistent with a narrowband signal from a point source at a great distance. But it was detected only once, has never been confirmed by subsequent observations despite multiple attempts, and its origin remains genuinely unknown. It might have been from another civilization. It almost certainly was not. The most likely explanations are natural or artificial, terrestrial in origin, though none of the proposed explanations is fully satisfying. The silence is not the result of a lack of effort. It is the result of sustained, systematic, increasingly sensitive effort over 65 years finding nothing. Now, there is an important caveat that I want to address directly, because I think it is sometimes used to dismiss the significance of the silence in a way that is not justified. The caveat is that the searches have covered only a tiny fraction of the possible search space. We have surveyed 1 million stars, but the galaxy contains 200 billion. We have covered a limited range of frequencies, but the electromagnetic spectrum is vast. We have searched for specific types of signals, narrowband radio transmissions, but civilizations might be using technologies we have not imagined. The silence might be silence of our searches, not silence of the universe. This caveat is real. The search has not been exhaustive. No serious SETI researcher would claim otherwise, but the caveat does not fully dissolve the significance of the silence, because the searches have not been random. They have been targeted at the most promising frequencies and the most promising stellar types. The 1,420 megahertz frequency was chosen for exactly the reason I described earlier, because any civilization with radio astronomy would know about it. The target stars were chosen based on their similarity to the sun and their proximity. These are not arbitrary choices. They are motivated choices that maximize the probability of detection if signals are being sent. Moreover, the absence of megastructures is not subject to the frequency range caveat. If a civilization built a Dyson sphere around its star, capturing a significant fraction of the stellar luminosity, the signature would be a star that emits too much infrared relative to its visible output. This is detectable across thousands of light years with infrared telescopes. We have surveyed hundreds of thousands of stars for this signature. The GAP project searched nearly 100,000 galaxies for the infrared excess that would indicate galaxy-scale energy use. They found nothing. A few candidate galaxies with anomalous infrared signatures were investigated and found to have natural explanations. If even one civilization in the history of the observable universe had built a Dyson sphere around a single star, we would have found it by now. The absence of Dyson spheres in our surveys is not a consequence of searching too narrow a frequency range. It is a statement about the absence of a specific and unambiguous signature. And it is the absence of that signature across hundreds of thousands of galaxies and billions of stars that I find most compelling. Let me take you now to something that I think is the most interesting and the most underappreciated aspect of the Fermi paradox. Not what the silence tells us about other civilizations, what it tells us about ourselves. If the great filter is ahead of us, if technological civilizations almost always fail to survive and expand, then we are currently in the most dangerous period in the history of our species. Not because of any specific immediate threat, but because we are at exactly the stage where the filter operates. We are a technological civilization that has achieved the capability to affect our own planet, to produce weapons of mass destruction, to alter our climate, to engineer biology. We are at the transition point that almost all civilizations appear to fail. And we know this. The silence tells us this is an extraordinary situation. We are the first species in the history of this planet to know that it is potentially dangerous to be exactly where we are. The dinosaurs had no warning of the asteroid. The organisms that died in the Permian extinction had no way to understand what was happening to them. But we have the Fermi paradox. We have the silence. And the silence, read correctly, is a warning, not a guarantee of doom, but a warning about the specific dangers of the transition we are currently making. The physicist Stephen Webb, in his book on the Fermi paradox, lists 50 possible solutions to the question of where everyone is. I have touched on several of them. But the one I find most compelling in the current context is what he calls the self-annihilation hypothesis. Not because it is the most comforting, but because it is the one most consistent with what we know about the development of technology and the specific dangers that technology creates. The self-annihilation hypothesis says that civilizations develop technology, reach a critical point of capability, and then destroy themselves. Not because they are stupid or malevolent, because the specific combination of capabilities that technology provides, the ability to release enormous amounts of energy, to engineer biology, to create systems of autonomous action that can operate faster than human decision-making, creates risks that are intrinsically difficult to manage. The risks are not hypothetical. We have already created nuclear weapons capable of ending complex life on Earth. We are already engineering organisms whose behavior in the wild is incompletely understood. We are already developing artificial intelligence systems whose decision-making processes are not fully transparent. These are not arguments for technological pessimism. Technology has also produced vaccines, clean water, and the infrastructure that keeps billions of people alive. The question is not whether technology is good or bad. The question is whether we can manage the specific risks that technology creates while continuing to benefit from the capabilities it provides. And the silence of the galaxy suggests that this is harder than it looks. These are not arguments for technological pessimism. Technology has also produced vaccines, clean water, and the infrastructure that keeps billions of people alive. The question is not whether technology is good or bad. The question is whether we can manage the specific risks that technology creates while continuing to benefit from the capabilities it provides. And the silence of the galaxy suggests that this is harder than it looks. I want to be more specific about what the hard part actually is, because I think the usual way of framing existential risk misses something important about the structure of the problem. The standard framing of existential risk focuses on specific catastrophic events: nuclear war, engineered pandemic, misaligned artificial intelligence, runaway climate change. These are real risks, and they deserve serious attention. But I think the deeper version of the filter, the version most consistent with the character of the silence, is not about any single catastrophic event. It is about the general difficulty of maintaining the institutional capacity to manage risk over the timescales required for a civilization to become long-lived. Managing existential risk requires sustained collective action over decades and centuries. It requires institutions that can coordinate the behavior of billions of people across national borders. It requires the ability to make long-term decisions that impose costs on the present for the benefit of the future. It requires the alignment of incentives across the full diversity of human actors, from individuals to corporations to governments to international bodies, around the common goal of survival. And it requires maintaining all of this coherence in the face of the competitive pressures, short-term thinking, and coordination failures that are built into the structure of any system of competing interests. This is not a technological problem. It is a political and social and psychological problem. The technology to avoid nuclear war exists. It is the decision-making systems that allowed nuclear weapons to be built and pointed at cities in the first place that are the problem. The technology to avoid the worst of climate change exists. It is the institutional failure to coordinate on implementing it that is the problem. Artificial intelligence will be developed by whatever organizations can develop it fastest and most profitably, not by the organizations that have the best plan for ensuring its long-term safety. The filter, in other words, may not be an asteroid or a supernova or a sudden technological catastrophe. It may be the slow, grinding difficulty of maintaining civilizational coherence in the face of the specific challenges that technology creates. The civilizations that survive are those that somehow develop the institutional capacity to manage these challenges over the centuries required for the transition to a stable, long-term configuration. The ones that do not develop this capacity slowly unravel. This is, I think, the most honest reading of the silence. Not that civilizations explode, but that they reach a level of technological capability that exceeds their institutional capacity to manage it, and they slowly deteriorate. I want to be clear about what I am claiming and what I am not. I am not claiming that human civilization is doomed. I am not claiming that the great filter is definitely ahead of us. I am not claiming that the silence proves any particular explanation. What I am claiming is that the silence is real, that the expected signal is absent, and that among the possible explanations, the ones that place a filter ahead of us are consistent with the data and deserve to be taken seriously, especially now, especially by us. Because if the filter is ahead of us, and if we somehow knew it was, the rational response would be to take every possible precaution against the risks that the filter might represent, to treat the management of existential risk as the most important problem we face, to organize our civilization, our institutions, our technology development, and our international cooperation around the specific challenge of surviving the transition that almost all civilizations apparently fail. This is not the dominant frame within which human civilization is currently operating. We are not, as a species, organizing ourselves around the hypothesis that we are at the point in our development where most civilizations fail. We are mostly operating as if the future is something that will take care of itself, as if technological development is automatically progress, as if the risks of advanced technology will be managed by the same ingenuity that produced the technology. The silence of the galaxy is telling us something different. Now I want to take you to the most recent developments in the search for technosignatures, because the field has changed significantly in the last decade, and the changes are relevant to the question of what the silence means. The traditional SETI approach focused on searching for intentional radio transmissions, signals that a civilization was deliberately broadcasting toward other stars. This approach was motivated by the same reasoning that led to the 1,420 megahertz frequency choice. If a civilization wanted to communicate, it would use the most detectable method available, and radio at the hydrogen line frequency would be the most detectable to any other civilization that had developed radio astronomy. But the broader concept of technosignatures, signatures of technology that might be detected even if the civilization is not intentionally broadcasting, has expanded the search space significantly. The James Webb Space Telescope, which I discussed in the video about the Hubble tension and lambda CDM, has the capability to detect specific molecules in the atmospheres of exoplanets. And some of those molecules, if detected in specific combinations, would be strong evidence of biological or technological activity. Oxygen in the presence of methane is particularly interesting. Oxygen and methane react with each other and would quickly destroy each other in the atmosphere of a lifeless planet. Their simultaneous presence in a planetary atmosphere requires a continuous replenishment process, which on Earth is provided by biology. Oxygen is produced by photosynthesis. Methane is produced by methanogenic bacteria and by the digestive systems of animals. If James Webb were to detect both molecules simultaneously in the atmosphere of an exoplanet, it would be compelling, though not conclusive, evidence of biology. Even more striking would be the detection of industrial pollutants, nitrous oxide, in concentrations above the natural background, chlorofluorocarbons, which have no natural production pathway, industrial nitrogen oxides at levels that cannot be explained by lightning or volcanism. These molecules would be unambiguous signatures of industrial activity. They would tell us not just that biology exists on a planet, but that technology exists, that a civilization has developed industrial chemistry. James Webb does not currently have sufficient sensitivity to detect these molecules in the atmospheres of most exoplanets, but its observations are providing data on the atmospheric compositions of a growing number of worlds. And the next generation of telescopes, including the extremely large telescope currently under construction in Chile, will have significantly greater sensitivity to molecular signatures in planetary atmospheres. The detection of an industrial pollutant in the atmosphere of an exoplanet would be the most significant discovery in the history of science. It would tell us that technological civilizations exist elsewhere, that we are not alone, that the Great Filter, if it exists, has not destroyed everyone. But it would also, depending on the planet and its history, potentially tell us something about the specific stage of development of that civilization and its current state. If we detected the atmospheric signature of a civilization that had been producing industrial chemicals for 1,000 years on a planet in our neighborhood, the silence of that civilization in the radio domain would itself be significant. A civilization that has had industrial technology for 1,000 years and is not broadcasting detectable radio signals is a civilization that has either not developed radio technology or has chosen not to broadcast. Both possibilities are interesting. The first would challenge our assumption that radio technology is a universal step in civilizational development. The second would be consistent with the sustainability solution, a civilization that exists but has chosen to remain quiet. I find this confluence, the possibility of detecting the chemical signatures of civilizations without receiving their signals, deeply interesting from the perspective of the Fermi paradox, because it could, in principle, allow us to distinguish between the scenarios. If atmospheric surveys find chemical signatures of biology and technology on multiple planets, the Great Filter in the past hypothesis becomes more likely. If the same surveys find no such signatures, the rare Earth hypothesis gains support. The next 2 decades of atmospheric spectroscopy, driven by James Webb and its successors, may provide data that changes the interpretation of the silence. The traditional SETI approach, focused on searching for intentional radio transmissions, signals that a civilization was deliberately broadcasting toward other stars. This approach was motivated by the same reasoning that led to the 1,420 megahertz frequency choice. If a civilization wanted to communicate, it would use the most detectable method available, and radio at the hydrogen line frequency would be the most detectable to any other civilization that had developed radio astronomy. But the broader concept of technosignatures, signatures of technology that might be detected even if the civilization is not intentionally broadcasting, has expanded the search space significantly. The James Webb Space Telescope, which I discussed in the video about the Hubble tension and lambda CDM, has the capability to detect specific molecules in the atmospheres of exoplanets. And some of those molecules, if detected in specific combinations, would be strong evidence of biological or technological activity. Oxygen in the presence of methane is particularly interesting. Oxygen and methane react with each other and would quickly destroy each other in the atmosphere of a lifeless planet. Their simultaneous presence in a planetary atmosphere requires a continuous replenishment process, which on Earth is provided by biology. Oxygen is produced by photosynthesis. Methane is produced by methanogenic bacteria and by the digestive systems of animals. If James Webb were to detect both molecules simultaneously in the atmosphere of an exoplanet, it would be compelling, though not conclusive, evidence of biology. Even more striking would be the detection of industrial pollutants, nitrous oxide in concentrations above the natural background, chlorofluorocarbons, which have no natural production pathway, industrial nitrogen oxides at levels that cannot be explained by lightning or volcanism. These molecules would be unambiguous signatures of industrial activity. They would tell us not just that biology exists on a planet, but that technology exists, that a civilization has developed industrial chemistry. The physicist Sarah Seeger at MIT has been leading research into exactly which combinations of atmospheric molecules would constitute the strongest evidence of life and technology, and her work has produced a catalog of potential biosignatures and technosignatures that James Webb and its successors could in principle detect. James Webb's first results on exoplanet atmospheres have been extraordinary in terms of the quality of the data, even if they have not yet produced evidence of life. The spectrum of WASP 39b, a hot Jupiter observed in 2022, showed clear signatures of water vapor, carbon dioxide, sulfur dioxide, and sodium, the most detailed chemical profile of an exoplanet atmosphere ever obtained. The detection of sulfur dioxide was particularly significant because it revealed that photochemistry, the chemical reactions driven by stellar radiation, was operating in the atmosphere in ways that matched theoretical models. This was not evidence of life, but it was evidence that James Webb can detect complex atmospheric chemistry in exoplanets with sufficient precision to notice unusual features. The planets that James Webb is best able to study atmospherically are the hot Jupiters and warm Neptunes, large planets close to their stars, because their extended atmospheres are easier to probe through transmission spectroscopy. The smaller, cooler, rocky planets in the habitable zones of their stars, the planets most likely to harbor life as we know it, are much harder. Their atmospheres are thinner, their signals weaker, their observation times longer. Current estimates suggest that characterizing the atmosphere of a potentially habitable rocky planet around a nearby star would require hundreds of hours of James Webb observation time, and the results would still be uncertain. But the capability is improving. The LIFE mission, a proposed European Space Agency concept for a space-based interferometer that would directly image the thermal emission from Earth-like exoplanets, would have the sensitivity to detect biosignatures in the atmospheres of dozens of nearby planetary systems simultaneously. It is not yet approved or funded, but the science case is strong, and the technical challenges, while significant, are not obviously insurmountable. The point is that the next 2 to 3 decades of atmospheric spectroscopy, driven by James Webb and the instruments that follow it, may produce data that changes the interpretation of the Fermi paradox fundamentally. If we detect chemical signatures of biology on one nearby planet, the rare Earth hypothesis is severely weakened. If we detect chemical signatures of industrial technology on one nearby planet, the question of the great filter becomes urgent in a completely new way. And if we survey dozens of potentially habitable planets and find nothing, that negative result will itself be informative, tightening the constraints on the frequency of life and technology in our galactic neighborhood. The silence we have observed so far is the silence of one specific search strategy, radio and optical signals, applied to a fraction of the accessible parameter space. The atmospheric search is a different strategy with different strengths and limitations, and it has barely begun. The next decade will tell us things that the previous 65 years of SETI could not tell us. Let me now take you to something that happened in 2017 that I think is directly relevant to the Fermi paradox, and that added a new dimension to the search for evidence of other civilizations. Something that generated more serious scientific discussion about the possibility of extraterrestrial technology than anything since the WOW signal, and that remains genuinely unresolved. In October 2017, an astronomer named Robert Warwick, using the Pan-STARRS telescope in Hawaii, detected an object moving through our solar system on a trajectory that was unmistakably hyperbolic. It was moving too fast to have originated in our solar system. It was the first confirmed interstellar object ever detected passing through the solar system. It was named Oumuamua, a Hawaiian word meaning approximately a messenger from afar arriving first. What made Oumuamua scientifically extraordinary, beyond its interstellar origin, was its anomalous behavior. As it receded from the sun, its trajectory deviated from what gravity alone would predict. It was accelerating away from the sun more than the gravitational model said it should. The standard explanation for this kind of non-gravitational acceleration in comets is outgassing. The release of gas and dust as volatile compounds on the comet's surface are heated by sunlight, but Oumuamua showed no visible coma, no detectable outgassing, no dust trail. It looked like a rock, not a comet, and rocks do not exhibit non-gravitational acceleration without outgassing. Its shape was also anomalous. The light curve, the variation in brightness as it rotated, suggested an object with an extreme aspect ratio, elongated or flat by a factor of roughly 10:1. This is unusual for natural objects. Most asteroids and comets are roughly potato-shaped, with aspect ratios of 2 or 3:1 at most. Harvard astrophysicist Avi Loeb proposed in a paper published in 2018 that the most natural explanation for the combination of non-gravitational acceleration, absence of outgassing, and extreme flatness was that Oumuamua was a thin, flat object being pushed by radiation pressure from the sun in the same way that a solar sail is pushed by radiation pressure. A solar sail of the right dimensions and mass would accelerate away from the sun at exactly the rate observed without any outgassing and would appear flat because it is flat. Loeb's conclusion was that Oumuamua might be an artifact of extraterrestrial technology, either a deliberately designed solar sail or a fragment of one. This proposal was not taken seriously by most astronomers. The conventional responses proposed various natural explanations. Hydrogen iceberg outgassing at levels too low to detect. Nitrogen ice from the surface of a Pluto-like body. A fragment of an exotic molecular cloud. Each of these explanations has its own problems. Hydrogen icebergs are not known to exist in the quantities required. Nitrogen ice evaporates and would produce detectable products. The molecular cloud fragment requires formation mechanisms that are not well established. None of the natural explanations is fully satisfying, and most require specific conditions that are not observed elsewhere. I am not claiming that Oumuamua was alien technology. The probability is low. The history of science is full of anomalous observations that turned out to have natural explanations once better data became available. But I am saying that the specific combination of anomalies in Oumuamua, the non-gravitational acceleration without outgassing, the extreme flatness, the interstellar origin, is not yet explained by any natural mechanism that has been proposed with full quantitative rigor. And I think the way the scientific community responded to Loeb's proposal is itself interesting from the perspective of the Fermi paradox. The proposal was dismissed by many researchers not because it was quantitatively refuted, because it was not, but because it invoked extraterrestrial technology, which is considered outside the Overton window of respectable scientific hypotheses. The cultural pressure against taking the technology hypothesis seriously, The same pressure that has distorted the SETI field in the ways I described earlier operates here too. The default assumption that anything anomalous must have a natural explanation, however unsatisfying, is methodologically reasonable in most contexts. But applied to every anomaly, it prevents us from even seriously entertaining the hypothesis that we might be seeing evidence of another civilization. A second interstellar object, Borisov, was detected in 2019 and appeared to be a normal comet by every measure. It had a detectable coma, a dust tail, spectroscopic features consistent with known cometary compositions. Oumuamua is not like Borisov. They are different kinds of objects with different behaviors. And the differences matter. The discovery of Oumuamua has prompted the development of new survey programs specifically designed to detect future interstellar objects earlier in their trajectories when they are still incoming and can be studied with more time and more instruments. The Vera Rubin Observatory in Chile, which began science operations recently, will have the sensitivity and cadence to detect interstellar objects far earlier than pan-stars could. If another Oumuamua-like object enters the solar system in the next decade, we will have weeks or months to study it, rather than the few days we had with the actual Oumuamua. And if it shows the same combination of anomalies, the case for a thorough investigation, including the technology hypothesis, will be much stronger. I raise Oumuamua not to claim it was alien technology, but because I think it illustrates something important about the Fermi paradox that is often overlooked. The search for evidence of other civilizations has focused almost entirely on signals, electromagnetic radiation deliberately or accidentally transmitted from other star systems, but there is another possible form of evidence: physical artifacts. Objects built or modified by another civilization that have ended up in our solar system through the dynamics of interstellar space. The galaxy is old. If civilizations have existed and expanded and built things, some of those things may have been scattered through interstellar space over billions of years, moving through star systems, occasionally visible from a planet that has developed the technology to observe them. We would not know they were artifacts unless they showed properties inconsistent with natural objects, which is exactly why the anomalies in Oumuamua are worth taking seriously, even if the probability of any specific object being artificial is low. The search space of physical artifacts is enormous and largely unsearched. We have barely begun to look. Let me now take you to what I think is the most profound philosophical dimension of the Fermi paradox, the deeper question of what it means to be alive in a universe that appears to contain no other minds like ours. There is a version of human history in which we eventually discover that we are not alone, that the galaxy teems with civilizations, that our situation is that of a child who has just been old enough to learn that other families exist. In this version, the silence is temporary. We have not found anyone yet because we have only just started looking, because our technology is too primitive, because the distances are vast. The discovery, when it comes, will be the greatest moment in the history of our species. It will transform our understanding of our place in the universe. There is another version in which the silence means what it appears to mean, that the universe is vast and old and largely empty of minds, that the emergence of intelligence capable of asking about its own origins and its own place in the cosmos is extraordinarily rare, that we might be, if not the only such intelligence in the observable universe, among a handful scattered across billions of light years, each isolated from the others by distances and timescales that make contact effectively impossible. In this version, the loneliness is real and permanent, not temporary, structural. I find myself unable to choose confidently between these versions. The data does not yet compel one over the other, but I notice that my emotional reaction to the two versions is very different. The first version is exciting. The second is sobering in a way that I find hard to articulate, but that I think is important to sit with rather than escape. If we are alone, or nearly alone, then the emergence of minds like ours is among the rarest things in the universe, rarer than stars, rarer than galaxies, rarer than almost anything the physical universe produces in the course of its evolution. And that rarity makes what we are and what we do here on this planet carry a weight that it would not carry in a universe teeming with minds. The physicist Freeman Dyson, one of the most original thinkers in the history of physics, and someone whose ideas I have always found worth taking seriously, wrote in his book, Disturbing the Universe, that the more he examined the universe and the details of its architecture, the more evidence he found that the universe, in some sense, must have known we were coming, not in a literal sense, not as evidence of design, but as an observation about the specific structure of the physical world and its relationship to the emergence of complexity and consciousness. The universe is the kind of place that produces minds. And minds that can understand the universe are extraordinarily valuable, regardless of whether there is anyone else to assign value. This is not an argument for human supremacy or for any particular cosmic significance. It is an observation about what the Fermi paradox implies if the silence means what it appears to mean. If minds are rare, if we are among the very few places in the observable universe where matter has organized itself into something capable of contemplating its own existence, then the continuation of that capability, the survival and flourishing of civilization, carries a weight beyond the merely local. The silence of the universe may be telling us that minds are precious, not because some external authority has declared them so, but because the data suggests they are rare, and things that are rare and fragile deserve to be treated accordingly. The silence of the universe may be telling us that minds are precious, not because some external authority has declared them so, but because the data suggests they are rare, and things that are rare and fragile deserve to be treated accordingly. I want to dwell on this for a moment, because I think it has implications that go beyond the abstract. If minds are rare in the universe, if the specific combination of physical, chemical, biological, and historical conditions that produces intelligence and self-awareness is something that happens in only a tiny fraction of planetary systems, then the emergence of mind is not the inevitable endpoint of a universal process. It is a fragile, contingent, improbable achievement. And the continuation of that achievement, the persistence of a civilization that has already passed through billions of years of prerequisite development, is not guaranteed by any physical law. There's a tendency in discussions of human civilization and its future to treat collapse or extinction as unthinkable, as something so extreme and so unprecedented that it need not be seriously planned for. We have survived everything so far, the argument goes. We have navigated every previous threat. We will navigate the next ones too. The species is resilient, but the Fermi paradox undermines this confidence in a specific way. Because the question is not whether any individual civilization is resilient. The question is what the typical outcome of civilizational development is across the galaxy. And the typical outcome, the silence suggests, is not long-term persistence, it is failure. Not necessarily dramatic failure, not necessarily the kind of sudden extinction event that produces obvious geological signatures, but failure to make the transition to the kind of civilization that would be detectable, the kind that lasts long enough and grows large enough to leave visible marks on the galaxy. If that is the typical outcome, then human civilization's resilience so far is not evidence that we will avoid the filter. It is evidence that we have not reached the filter yet. The filter is ahead, at the transition from a technologically capable but institutionally fragile civilization to a stable, sustainable, long-lived one. And the specific capabilities we have developed in the last century, nuclear weapons, biotechnology, artificial intelligence, climate-altering industry are precisely the capabilities that make the transition difficult. They are not the cause of the filter. They are the test. I want to say something about what the filter might look like from the inside, because I think understanding that changes the way the silence feels. A civilization approaching the filter does not necessarily look like a civilization in crisis. It might look exactly like our own. Rapidly growing technological capability, expanding global communication, increasing standard of living for large populations, unprecedented scientific understanding of the universe. These are all genuine achievements. They are not signs of failure, but they coexist with the specific risks that the filter represents. The weapons capable of ending civilization that have been produced as byproducts of the same physics that enables nuclear medicine. The climate disruption that is the byproduct of the energy systems that enable global prosperity. The artificial intelligence systems that are the byproduct of the computational capabilities that have transformed medicine, communication, and scientific research. The filter, if it is real, is not something that destroys civilizations despite their achievements. It is something that emerges from their achievements. The same physics, the same chemistry, the same computational capabilities that produce the highest achievements of civilization also produce the highest risks. Managing the risks without abandoning the achievements is the test. And the test is hard. This is what I think the Fermi paradox is really about. Not whether aliens exist or whether they would be friendly, but what the history of civilizational development in the universe tells us about the specific challenge we are currently facing. The silence is not just an astronomical datum. It is a statement about what happens at the specific stage of development we have reached. And the statement, read honestly, is not reassuring. But I want to be careful not to leave this on a note of pure doom, because I do not think doom is the right conclusion. The silence tells us that the transition is hard. It does not tell us that the transition is impossible. The fact that we have reached this stage of development, that we are the specific civilization asking these questions at this specific moment, is itself significant. We are here. We survived whatever preceded this moment, and we have something that most civilizations that ran into the filter apparently did not have or did not develop in time. We have the knowledge of the filter itself. We know about the Fermi paradox. We know that the silence is telling us something. We know that the transition we are currently making is the most dangerous period in the history of our species, not because of any specific immediate threat, but because of the general structure of the challenge. And knowing that, being able to name the specific danger with scientific precision is not nothing. It is the beginning of the ability to respond to it. Every civilization that ever destroyed itself did so, presumably, without knowing that the silence of the galaxy was evidence of what was coming. Without knowing that the specific combination of capabilities they had developed was the test that most civilizations failed. Without having the Fermi paradox as a warning, we have it. Whether we will use it is a different question, but we have it. I want to come back to the specific character of the silence now. The silence has a particular texture that I think has not been adequately appreciated in most discussions of the Fermi paradox. The silence is not the silence of a universe that tried and failed. It is not the silence of a universe that never started. It is the silence of a universe that by every indication of the physics should be full of detectable signals and structures, and yet is not. The specific form of the silence, the absence of exactly the things we would expect if civilizations were common and expanding and long-lived, is itself informative. What we would expect if civilizations were common and expanding is not just signals. We would expect to have been visited. We would expect that the material composition of our solar system would bear the marks of prior intervention. We would expect to find artifacts in our solar system that were not produced by natural processes, We would expect the distribution of stars and planetary systems in our galactic neighborhood to show signs of engineering. We would expect, in short, a galaxy that looks like it has been inhabited. Instead, we find a galaxy that looks, to every measurement we have made, exactly like a galaxy in which no one has ever done anything large scale. No megastructures, no redirected asteroids, no stellar engineering, no artificial objects in our solar system that were not put there by us. The stars move on their gravitational orbits without any indication that anything has altered those orbits for any purpose. The gas and dust of the interstellar medium are distributed exactly as the physics of star formation and stellar winds would predict, without any sign of large-scale manipulation. This is the most complete version of the silence. Not just the absence of radio signals, the absence of any large-scale consequence of the existence of prior civilizations. And this form of the silence is the hardest to explain by the searches are too limited argument. Because the absence of megastructures, the absence of stellar engineering, the absence of any sign of large-scale civilizational activity in the structure of the galaxy is not a failure of our radio receivers to pick up the right frequency. It is a statement about the physical state of the galaxy as a whole. The galaxy has not been organized, it has not been managed, it has not been used. It looks like a natural system. And natural systems, in the ordinary course of things, do not produce beings capable of building megastructures. So either beings capable of building megastructures are extremely rare, or they exist but choose not to build them, or they exist and build them, but something consistently prevents them from persisting long enough to leave permanent marks on the galactic structure. This third possibility, the one in which civilizations reach the capability to affect the galaxy but then fail before leaving lasting marks, is the one I find most consistent with the specific character of the silence, not the absence of intelligence. The absence of intelligence that persisted. The silence is the sound of civilizations that stopped, that got to the edge of the transition and did not make it through. And we are at the edge of the transition. Let me close with something that I think is the most important thing I can say about the Fermi paradox and what it means for us right now in this specific moment. We are the first generation of humans who knows about the Fermi paradox and understands its implications. We are the first generation for whom the silence of the universe is a data point rather than an unexplored question. We are living at a moment when we know enough about the physics and the biology and the statistics to understand what the silence means, even if we cannot yet conclusively interpret it. And we are living at the specific point in civilizational development that the silence suggests is the most dangerous. I do not say this to frighten. I say it because I think knowing it changes something. When we understand that the silence of the universe is not just an astronomical puzzle, but potentially a warning. Something in the way we think about our own choices and our own civilization shifts, not into fear, into responsibility. The civilizations that filled the galaxy with signals and megastructures and the unmistakable signs of their existence, they are not here. The civilizations that are quiet, that exist sustainably within their planetary systems, that did not expand to the point of detectability or did not survive to do so, they are the ones we cannot detect. The ones we know about are the ones that made it, and there are apparently very few of them, or possibly none at all. We do not know yet which kind of civilization we will be. The silence does not tell us our fate, it tells us our situation. And our situation is that we are at a critical juncture in a story that has apparently been told many times before and has very rarely ended well. The silence of the universe is not empty, it is saturated with absence. The absence of the transmissions that should be there, the absence of the megastructures that should be there, the absence of the visitors that should have arrived. By the logic of the distances and the timescales and the physics, that absence is data. It is the most important data we have about the likely fate of technological civilizations. And one of those civilizations is us. Go outside tonight. Look at the sky. The darkness between the stars is the silence I have been describing. Not the silence of nothing. The silence of something that should be there and is not. The silence of every civilization that started the transmission and then stopped. The silence of every signal that was sent toward a civilization that no longer existed when the signal arrived. The silence of every planet that produced intelligence and then, for one reason or another, went quiet. The signal we have been sending, our radio broadcasts, our radar emissions, the electromagnetic signature of our civilization has been propagating outward into that silence for about 100 years. At the speed of light, it has now reached stars within 100 light years of Earth. There are roughly 15,000 star systems within that sphere. If any of them has a civilization with receivers sensitive enough to detect the leakage radiation of our broadcasts, they know we are here. We have not heard back. Not yet. Perhaps there is no one to hear back. Perhaps they are listening too, pointing their own receivers at us, waiting for a response to a signal we have not yet detected. Perhaps the message is coming and it has not arrived. Or perhaps the silence is the answer. And the answer is that in a universe this old and this large, minds like ours are rare, and rare things are precious, and precious things deserve to be protected. That is what the silence of the universe is telling us, if we are willing to listen. If this changes how you hear the silence, if the night sky sounds different after this than it did before, tell me in the comments. Tell me which explanation for the Fermi paradox you find most compelling and why. Tell me whether the silence frightens you or galvanizes you. These conversations matter. And subscribe if you want to stay at the frontier, where the physics of the universe meets the questions that matter most for the future of the one civilization we know for certain exists.